the ways of handling confounding or controlling for confounding. So there are confounders. One thing you should understand is confounders are there. How to differentiate between bias and confounding is bias is an error which you make because of which bias comes in your study. Confounders exist. You have to control those confounders. Effect modification exists. If it is there, you have to report effect modifiers. So you do different things to these different concepts. So confounding in the design phase, restriction and matching, and in the analysis phase, the three methods are standardization, stratification, regression, and some newer techniques which are coming up. Just introduce it as we move ahead. So restriction means what? I limit my study population to one category or strata of the potential confounders. So in my inclusion exclusion criteria, I specify. For example, if I'm looking at diabetes and treatment, TB treatment outcome, and I feel that BMI is a potential confounder, I say that I will do study only in people who have normal BMI, patients who have normal BMI. That is restriction. So now one thing I should tell you all is that if there is a potential confounder, the confounding happens if the distribution of this potential confounder is different in your comparison groups. If the distribution is the same in the two groups, there will be no confounding. Or if I study only one subgroup, like in this case, there will be no confounding. So one way of negating confounding is to just stick to one subgroup of the confounder. So I am just looking at all those who have normal BMI and I am looking at the association. There will be no confounding of BMI in my study. That is restriction. So this is simple to implement and there is nothing to do in the analysis actually. But of course, generalizability, your findings now are limited to those with normal BMI. Then it doesn't mean that you do not have to collect data on confounders. Still, you have to take the height, weight, and the BMI to ensure that the patients meet your eligibility criteria. And then, of course, it is going to restrict the numbers, the sample size, more efforts to meet the sample size, which is true with restriction. So restriction is one method of handling confounding, of ensuring that there is no confounding because of a variable in your study. The next is matching. Now, these star marks which I have put for each of the headings is just to tell you all that each of these is a topic in itself. These are topics which need to be read in detail. We are just introducing them as methods of controlling confounding. So matching is what? You select one or more than one control which are similar with respect to the case for the potential confounders. So if age and sex, these are common confounders. So if you have a person as in the intervention group, as in the intervention group who is a male, you will have a male in your control group. So it is 1:1 or individual level matching which you do. Similarly, in your case control study, if you have chosen a case who is a male, you will have to choose a control who is a male. So that is individual level matching. You can also have group or frequency matching. So you have to first select your cases or your intervention group, study the distribution of the confounding variable, what is the distribution, what are the proportions, and then you select your control group such that the distribution of the confounder is similar in your control group. This is frequency or group level matching. There are two ways you can do matching. Now, what is important in matching is that just by doing matching in your design, you are not going to control your confounding. Matching in the design should be accompanied by matched data analysis. This is very, very important. If you are doing matching, especially this 1:1 matching or individual level matching, you have to ensure that you do special kind of analysis, matched data analysis. If you do not do so, then you are not eliminating confounding and you will underestimate the association of the exposure and the outcome. So This is true for individual level matching, but if you're doing group level matching, you need not do matched analysis. So one take home message is, if you do matching in the design phase, then you have to compulsorily do a match analysis, especially and truly for individual level matching. So matching helps us to negate the effect of the potential confounders. Any questions? So what are the advantages of matching? Actually, what matching does is it increases the efficiency of the study or the power of the study to detect the effect if it exists in the study. And confounders that are difficult to measure. So many a times there are many confounders, and sometimes some of them are difficult to measure. You can just have a neighborhood matching and say that we have matched for environmental factors or socioeconomic factors. But there are logistical difficulties in recruiting matched controls. And once you do matching for a variable, you cannot study its effect on the outcome. And if you do not do a matched analysis and are not careful about matching and doing your study properly, you can in fact introduce a selection bias in your study. So when you're doing matching, you have to really read about it and understand how you should do matching in your study, and then match it up with a proper analytical framework. The next is randomization, which is usually done in intervention studies, where you randomly assign exposure intervention, the individuals, you assign them into these two groups. And then you know that one important strength of randomization is that you are controlling for known as well as unknown confounders. This table 1 in a randomized control study is very important because it helps us to check how successful you have been with your randomization in making the two groups comparable to each other with respect to your confounders. Randomization, of course, cannot be done in observational studies, and it needs large numbers. If you do randomization for small groups, it will not make the two groups comparable. So sufficient numbers are required. And then, of course, there are ethical limitations, especially only when there is equipoise, you can do randomization. So this, I think, many of you already know in detail about randomization. So these are the three, or these are different ways in which you try to control for confounding in your design phase. Now, what happens in your analysis phase? If you do not use any of the methods, still you can control for your confounding in your analysis. So what are the different ways? One is stratification. So you stratify by the confounder. So the expectation is that the effect of the confounder will be removed in each of the stratum, and you get a effect which is free of confounding in each of the strata you have considered. So remember that the strata, if it is too narrow, if you have very like a narrow strata cutoffs, class intervals, you can have small numbers in each strata. If you have too broad, then they can become similar to each other and there will be residual. So I'll be talking about residual confounding in the upcoming slides. And then if you do not measure the confounders, or if you do not create the strata, effective strata or correct strata, both of this can lead to residual confounding. So even if you say that you have done stratification to handle confounding, still confounding may remain if you commit these errors in your method section. So this I'll come back when we look at confounding stratification in detail. So this is one example in which we are looking at the association of alcohol consumption and myocardial infarction. Now this odds ratio of 2.26, this is a crude odds ratio. So as I said, the first step in stratified analysis is to calculate the crude odds ratio. Then the next step is to identify the two strata for your confounders. For this association, I am again looking at smoking as a confounder. I have two strata, smokers, non-smokers. So I calculate stratum specific odds ratio. So for both smokers and non-smokers, I got an odds ratio of 1. So my second step was to calculate the stratum specific odds ratio for the two strata of the confounders. The next step is to compare the stratum specific odds ratios. 1 and 1, they are equal. Sometimes they need not be equal. They can be nearly equal to each other. So when they are nearly equal, you can calculate a weighted measure of effect. Now, for the odds ratio, that is known as a Mantel-Hansel odds ratio. Now, this is a formula. Again, this itself is a different topic. I am not going to go into detail, but you can calculate the weighted average of the effect and you get it as 1. Now you compare this, the weighted average of the stratum specific odds ratios with the crude odds ratio. So you have to compare 2.26 and 1. Now these are not equal to each other. It means smoking is a confounder for the association of alcohol and myocardial infarction. If the stratum specific odds ratio were similar to each other and the weighted average would have been 2, which is approximately equal to your crude measure, you would have said that there is no confounding. Are you all getting me here?
Yes, ma'am.
Yes, ma'am.
Yeah. So in stratification is one method to assess whether the variables which are there with you, which you have collected, are confounders, are confounding the effect of exposure and outcome. Step 1, estimate crude measure of association. Step 2, estimate stratum specific measures. Compare the stratum specific measures. If they are similar or nearly similar to each other, calculate a weighted measure. Compare the weighted and the crude measure. If they are similar, no confounding. If they are not similar, then you say that there is confounding and that confounding has to be adjusted, means you do not, you report your adjusted or your weighted measure. Then the another way of handling confounding in your analysis is standardization. Again, this is also taught in your undergraduate days. So there is direct and indirect method of standardization. Again, this is a separate topic. We won't go into it. Only one point, that you can standardize for age, you can standardize for sex, you can standardize for both of them together. Or remember that you can also standardize for other variables. This is the only thing which I wanted to tell with regards to standardization. Then regression. Again, in the opening itself, somebody had mentioned that yes, regression is a method of handling confounding. So stratification, what is the limitation of stratification is that if there are one or maximum two variable, and if they are categorical or more so binary, it is easy to do stratification and check for confounding. But if your variables are continuous variables, or if there are multiple variables, then stratification will not help you. The only way possibly you could handle your confounding is through regression, where then you will get an adjusted estimate of the association of the exposure on the and the outcome. So many times you will see that majority of the studies then rely on regression without going into other methods in the analysis section. Now there is this another method which is recently you will see in literature, propensity score method. Now I will not go into this method because again I am showing that this is a star mark. This is a separate topic in itself, and we need to really understand this in greater detail. So actually you have the risk factor which is stratified according to a distribution of other covariates, and then you just have this the strata of the risk factor, and you study the association of these different strata with the outcome. So just remember the name. I will not go into the details because we will, if possible, take a separate section on this method of propensity score method for adjusting for confounding. So when you're looking at your analysis phase, you have to first, what are the different ways? I told you we will come back and see how you can handle your confounding in the analysis phase. So one option is to say, decide a priori that these are going to be my confounders. So there are two confounders you will see in many studies. They are considered a priori as confounders. These are age and gender or sex, right? So for majority of the associations, these are confounders. So you say, whatever my analysis shows, I will still retain them as confounders in my analysis, usually regression. Now you have to assess how the confounders behave in your data set. Aruna, do you have a question? Okay. So you have to include all the potential confounders in the analysis. Now, one thing could be you compare your crude and your adjusted measures of association, just like what you did in your stratified analysis, and you check whether they are similar or nearly similar to each other. If yes, you say there is no confounding. If the crude and the adjusted estimates are different from each other, you say that there is confounding and you comment on the confounding in your interpretation section. So I told you one method is a priori, age and sex. The second thing is to look at the DAGs based on the theory and finalize your potential confounders. The third way is you look at your potential confounders. You have your regression model. You have the exposure and the effect, the outcome and the effect in your regression model. You keep on adding your potential confounders and you see the change in the strength of the association. How much change is there in the measure of effect? If there is a drastic change in the measure of effect, then the value or the variable which you have added is a confounder. It is confounding your association. Or you compare your adjusted and the crude or the unadjusted estimate. As I told you earlier, that also helps you to assess confounder. And the a very important sentence, the last sentence, that there is no statistical test which helps you to identify confounding. So there is a lot of subjectivity in confounding. You have to decide whether confounding is present or not without any statistical test. There is no statistical test which is going to help you to say whether confounding is there or not. So usually it is said that if there is a difference of, in some books it will be written more than 10%, some books 15%, some books will say a 20% difference between your crude and your adjusted estimates, then you say that there is a potential confounder. So again, you see, there is nothing hard and fast or a rule as such, but in your methodology, you could say that this was the cutoff which you considered when you compared your adjusted and crude values, or when you added a variable into the model and your measure of effect changed by more than 20%, you could think that, okay, there is confounding. But the take home message is there is no specific statistical test to check for confounding or to help you decide whether confounding is present or not. So this is one thing which you should remember. So again, for stratification, just to make things clear, first step is crude estimate, then adjusted estimate, compare the crude and the adjusted estimate. If they are similar, no confounding. If they are different, there is confounding. And this similar, not similar, again, there is, I told you, this books can mention 10, 20, 50% dissimilarity to decide whether confounding is present or not. Again, an example. So you have crude and you have adjusted estimates. If the crude and the adjusted estimates are similar to each other, like here, there is no confounding. Again, here the crude estimate is 2 and your adjusted estimate is 1.7. They are nearly similar to each other. So no confounding here too. And your crude estimate is 2. Your adjusted estimate is 1.2. It appears to be different more than, say, if your cutoff is 10%, 15%, 20%. So yes, this particular factor which you have adjusted for is a confounder for the association for exposure and outcome. This is the way you can decide about your confounding without a statistical test. You all are with me here?
Yes, ma'am.
Thank you, Sampath. So now, coming to this example, a publication where it studied the association of alcohol beverage consumption and lung cancer risk. Now, this actually, this was, yeah, this I have made a mistake out here by taking, okay, correct, it's correct, sorry. So the exposure here is alcohol beverage consumption and the lung cancer risk. So I want somebody to interpret now this table, what you see here. This is the way you will be reading articles, and whatever has been covered till now should help you make an interpretation. So how would you interpret the findings which are presented in this table?
Ma'am, I just got that unadjusted odds and adjusted odd ratio is there, ma'am. There's a reference and there is +1 drinks per day.
Yes,
So in
correct,
first table 2.6, ma'am, and second is 1.6. So there is
correct.
a difference, as you said, ki so many books have 10-20%. So this difference is more than that. So we can say that in this example there is confounding.
Yes, but confounding by what?
Confounding by what, ma'am? With
Look at the footnote.
per year, ma'am. Per
Look
year
at the footnote. Look at the footnote.
smoking.
I am
Confounding
highlighting.
by age, race, sex, indicator variables.
Yes, Dr. Apurva. Sampath, you are right. You have correctly looked at these values, the unadjusted and the adjusted odds ratio. You have compared the two, and you have correctly said that there is a difference between the two, so there is confounding, right? So it's important to look at the entire table, look at the footnote, because after adjusting for age, race, sex, and there are some lab tests which were done for saturated fat, then for smoking. So when there was adjustment done for these potential confounders, you see that there is a change in the adjusted odds ratio. So these variables have confounded the association between alcohol consumption and lung cancer risk. So in this table, what do you see? That never to 3 drinks per month is the reference. 1+ drink per day is the exposure, right? So how would you interpret in a sentence? Supposing this 1.60, ultimately now you are interested in 1.60. So how would you interpret?
People who drank more than 1 drink per day had 1.6 times higher risk as compared to people who did not, drank less than 3 drinks per month.
Correct. But this should always be accompanied with the rest of the sentence after adjusting for age,
Yes, ma'am.
race, etc., etc. And then this 95% confidence interval, this p-value, this tells you that this association is not significant. So association which was significant earlier in the crude estimate, when you adjust for confounders, it reduces the strength of the association and it is no longer significant, right? So the effect of alcohol consumption is no longer significant on the risk of lung cancer after adjusting for all these variables. So this is something, this interpretation which I have written here is basically for you all to understand that you have to write the complete sentence. That is after adjusting for the potential confounders. Now, what do you think? Is there all of these different potential confounders, are they having a positive or a negative confounding effect?
Ma'am, negative, because first it was significant and then the odds ratio decreased and became insignificant.
Okay. So just keep this with you, Dr. Anjana. We will come back to the positive and the negative effect and come back here. I think the next slide itself is about it. Not the next. I think it will come in the coming up slides. Now this next point is that remember that you have the exposure and the outcome, right? So you have the exposure and you have the outcome, and in your study might be body mass index is the potential confounder, but next time you do the study, some other might be some other person who takes up the study, or you do the study, body mass index becomes your exposure and your outcome is TB treatment outcome. Now diabetes mellitus can become your confounding factors. So there is no hard and fast rule that body mass index will always be a confounder. Remember your age, sex, your socioeconomic status, all of these can be your exposure. They need not always be potential confounders. So depending upon your research question, your variable can be either an exposure, an outcome, or a potential confounder. This is what I want to tell you all with this particular slide. So don't ever think that age and sex can always only be your confounders. Now here is the one which Dr. Anjana. So the crude estimate is close to the null value compared to your adjusted estimate, right? So crude is here and adjusted is far away in either direction, positive or negative. That is a negative confounder. And your adjusted estimate is close to the null and the crude estimate is far away from the null. That is positive confounding, right? So what did Anjana tell us about this crude and I'm sorry, crude and your adjusted? So Anjana, can you explain now? You have the null value.
Yes.
Where was your crude? Positive, away from the null,
Crude is,
and adjusted is near the null
yes,
compared, right? So what kind of
yes,
confounding is this?
positive.
Yes. So you were right? You said positive, no?
No, ma'am, I told negative, but
Oh,
I
sorry,
realize now.
sorry. Okay, so please correct yourself then. So what you do if you want to write in your
Okay.
discussion that this has a these different variables had a positive or a negative confounding, what is the step? Compare the crude and the adjusted. If the crude is nearer to the null value compared to the adjusted, it is a negative confounding. If the crude is away from the null compared to the adjusted, it is positive confounding. The confounders are increasing the magnitude of the effect, that is positive confounder. You're getting me, Anjana?
Yes, ma'am.
Yeah. So when you're looking at confounding, you have to understand that right from the time you plan that this is my exposure, this is the association I'm interested in, you should start thinking about potential confounders in your planning phase itself. Collect data for the confounders, decide whether what you can do in the design phase and what you're going to do to handle the confounders in your analysis. Then again, there is a concept of unmeasured confounding. So when especially you are relying on secondary data, which is already there, you know that there are so many confounders, but that data has not been collected. Then you have to remember that there is unmeasured confounding, which you have to mention as a limitation of your study. Residual confounding, which I mentioned earlier, is when you are using some proxy measures as a representation of your confounding, or Instead of age, you convert the age into age groups, or you are not measuring the confounder accurately. There is measurement error in measurement of confounding. Your strata which you are making are too broad. For example, age groups you are making too broad so that people are more similar to each other across the age group. If any of this is happening in your methods, in your handling of the data, then you should mention residual confounding as a limitation of your study. Now here is another example. So again, it is up to someone in the group to try and read the table and give an interpretation. So whenever you are reading the table, what is the trick? The trick is first to read the title. Association of oropharyngeal cancer with exposure to HPV and with biomarkers of cancer associated with HPV 16. Then look at the headings. So this is measure of HPV exposure or disease. So seropositive and seronegative for HPV 16 L1 serologic status. Then they have given the cases and the controls. This appears to be a case control study for 100 cases, 200 controls. And how many of the cases and controls were seropositive. And measure of association in this case control study is the odds ratio, the unadjusted and the adjusted. The reference is seronegative, and for the seropositive, you have the odds ratio. So now can anyone interpret? So what remains is interpretation of the odds ratio. Another hint I gave you all, always look at other parts of the table, the footnote. Can anyone volunteer, please, to interpret the odds ratio?
Ma'am, the odds of all those potential confounders, there is no association among seronegative and seropositive of HPV 16L1 serologic status.
No, please look at the values carefully, Anjana. The
Hello.
odds ratio is 17.6 and 32.2.
Ma'am, after adjusting for the potential confounders, the people who had HPV positive, the seropositive patients, had 32.2 times higher risk of oropharyngeal cancer as compared to the seronegative ones.
Yes, right. So when you look at the crude, means you're not adjusting for the confounders. The risk is 17.6 times more in those who are seropositive compared to those who are seronegative. When you adjust for age, sex, tobacco use, alcohol use, dentition, toothbrushing, presence of family history of head neck cancer, what happens? After adjusting for potential confounders, the risk is 32.2 times more in those who are seropositive for HPV 16 compared to those who are seronegative. Am I right, Dr. Anjana?
Yes, ma'am.
I think you were just concentrating on this confounding. So you have the null value.
Negative, ma'am.
Negative.
Okay, good, Abhishek. So you have the null value, you have the crude value, and you have the adjusted value, which is here. So the crude value is nearer to the null value compared. So this is negative confounder, right? So it is underestimating the association. After you adjust, you get the higher value. So it is negative confounding. Now, another question I have for you is this. These were the different potential confounders which were taken up in the study. So data for all of this was collected in the study, right? But you will see that some of these variables were not included in the regression. This is multiple logistic regression they have done. Only the ones which are, so they have adjusted only for these. For example, education, ethnicity, home state has not been included. So can you guess why this has not been included in the regression model?
Unadjusted values were not significant for them.
Great. Yes, Dr. Abhishek. So what they did is they have probably checked and they have set some criteria for including the variables in the model to consider them as potential confounders. These variables did not meet those criteria, so they have not included these different variables. So you will have to collect data on more variables. And if you want to assess confounding in your study, you will have to do some kind of analysis to decide that yes, out of these different 15 variables, only 5, 6, or up to 10 or whatever variables appear to be having potential confounding for the association in my data set. So I will adjust for them. This is one way of handling confounding. So this is something again you need to remember. The next thing is again some more examples. So this is one study in which alcohol and lung cancer risk was done among never smokers. So which method of controlling confounding was used here? It is a method which is done in design phase of the study.
Restriction, ma'am.
Restriction.
So restriction. So restriction was a method. So they have said, okay, let me not do this smoker, non-smoker thing. Just let me do in one strata of the confounder. Now, when you are reading articles, you will see some sentences like this, which are all ways in which the investigators have tried to handle confounding. So I'll just read them out. All variables that were either statistically significant in univariate analysis were included in logistic regression. So this is what Dr. Abhishek mentioned. So all those who had a p-value less than 0.05 in the univariate analysis, I am going to take them up in my multiple variable regression model. Then the authors also say, or potentially important with respect to prevention. What I'm trying to tell you is that in your method section, you can say that yes, one criteria is to say that the ones which are significant in the univariate analysis, and irrespective of what the univariate analysis is, still a priori, I am saying that I am going to include these other variables like the use of gloves, taking zidovudine, etc. in my multiple regression. I'm going to still include them as potential confounders. This is one way of deciding about your potential confounders. Then another article which says the odds ratio and the 95% confidence interval were calculated using the univariate logistic regression models. In addition to basic variables such as age and sex, those again the same thing, right? So here, which are the a priori variables? Age and sex. In addition to these variables, others which were significant were included in multiple logistic regression analysis. So this is one way of handling confounding and then mentioning it in your methods section. Some more examples. So in one study, it is mentioned initial regression models included age and menopausal status. Given their strong association with breast cancer, additional potential confounders were tested individually if the risk estimate associated with smoking changed by 10% in either direction, we included it in the full model. So what they did, they had a model in which you have the outcome, the exposure, age, and sex, and they kept on adding other potential confounders, and they looked at this association between the risk factor and the outcome. And if after adding the variable, if this changed by more than 10%, they retained it as a potential confounder. This is another way of deciding on confounding. And then, of course, you have this backward, forward, stepwise regression, which is a big question mark because there is a lot of controversy about these methods. And you have to use it sparingly, very carefully, because it has some issues which are there if you just rely on these the statistical algorithms to decide what is to be included in your regression model. So this is something which is also exists. It appears to be very exciting, interesting, but you have to be careful before deciding on using these stepwise regression techniques. So again, because one of the PG students in my department was discussing about the stepwise techniques, that is a forward, backward, stepwise, which includes both forward, backward selection, I just wanted to reiterate that instead of using any of these methods, purposeful selection, that is stating that these are my a priori um, potential confounders, and then I am going to do a univariate analysis and I am going to check whether it brings about a substantial change in the association between the exposure outcome, or in the univariate whether the p is less than 0.05. So some such criteria where there is application of knowledge and you have clearly stated what you are going to do from your side, that is a better idea for handling confounding rather than just relying on statistical algorithms like these selection techniques, is a suggestion which I wanted to give. So I think I'll just break here, because what I wanted to do, if people are interested, to really tell you all in a software exactly what happens, what are the steps, including the stepwise uh, regression, if you all are interested in. Otherwise, I'll wait here and take up questions if you have any questions. Dr. Joyce, are there any questions in the chat? You can write your questions in the chat box or you can raise your hands. Any questions about? Yes, Dr. Neha.
Not question, ma'am, but would be interested to see the statistical analysis.
Yes, so not all will want to wait because it's more than 1.5 hours now. But those who are genuinely interested, we will go through the steps. Any questions? Anyone has any questions about, particularly about confounding? So what we did was we began by understanding the differences between confounding, effect modification, interaction, and mediation with examples. And then we saw the concept of confounding, different ways of understanding confounding. Then what are the ways of identifying potential confounders in the, based on the literature, based on the knowledge you have, your expertise or consulting experts, or then in your, even in your data set, how you can identify confounders, and then how to control for confounding, adjust for confounders in your design, in your analysis phase. That is what we have done. And then when you are interpreting, always remember that when you're reporting your adjusted values, never forget at least somewhere to mention that you have adjusted for all these potential confounders to get your adjusted values. Adjusted means what? It means that you are now controlling for the confounders in both the groups and you are making them similar to each other and then coming up with the adjusted value. So you are controlling for confounding is what adjustment means. Any questions?
Ma'am,
Ma'am,
no questions in the chat.
I want to ask one thing.
Yes.
Ma'am, can we ever truly remove this confounding just statistically, or ma'am, or does it presence always indicate a deeper problem in study design? Like, ma'am, we say variable measurement, or we can just partially adjust for it, or we can remove it. Like, I'm getting
See,
confused, ma'am.
yeah, see what happens, there will be innumerable confounders. You will have to identify at least the major confounders, right? But still there could be some confounders you are not aware of, or for which data will not, cannot be collected. So there will be unmeasured confounding. Even when you are collecting data on confounding, if there are errors in measurement, there will be residual confounding. You collect data, but you need to categorize them. If you're categorizing them very broadly or wrongly, there will be residual confounding. But you try and handle or control for confounding as much as possible, right? So there is always possibility of unmeasured residual confounding, but you have to attempt to control for major confounders to get a true estimate of the effect of the exposure on the outcome.
Okay, ma'am.
But there is nothing wrong in the study design. Remember that the confounding exists in nature. It is there, out there. It is not your mistake that confounding is there. It is not the mistake of the investigator that confounding is there. It is there. You are trying to control it. If you do not control it, if you do not acknowledge that, okay, confounding is there, I am collecting data on it, I'm controlling for it, and then I am finding this. This is all the investigator can do. You cannot just remove or cannot, it's not you who have brought in the confounding.